My name is Pedro Guaranha, and today I'm going to present the work developed by my colleagues and I, that is the evaluation of the WSGG model for couple calculations of laminar flames. So, most work in literature, they tend to analyze the radiation field in a decoupled state, that is, with predefined values of temperature and of molar concentrations. So the idea of this work is to take the Chem1D software, that is a software for calculating one-dimensional flame structures, and implement two methods for solving the radiative heat transfer equation. That is the line-by-line integration and the weighted sum of gray gases model. The latter one having the possibility to implement different formulations of the proposed coefficients. And then the idea is to evaluate and compare these different propositions of the WSGG and the LBL method. So, going a little bit about the equations, for a medium that absorbs and emits radiation, but scattering is neglected, the radiative transfer equation is given on the right. And integrating it over all the spectrum will result in the total absorbance along a uniform path. So, taking for example a single broadened line, this result is null almost everywhere except in a narrow wave number range surrounding this single line. The weighted sum of gray gases then represents the spectrum in its entirety with only a few gray gases with uniform pressure absorbance coefficient plus a transparent window. And it allows for changes in molar concentration and temperature to be accounted for in the partial pressure term and on a temperature dependent coefficient. And this determination of these coefficients that varies from author to author, with each using the fitting data best responded to their benchmark comparisons. So the L by L method stands today as a benchmark solution of spectral dependency. They can be considered exact except for some minor numerical approximations in the integration. And this model was based on the discretization of the wave number for the spectral properties. They are available in the extensive database of the HiTem 2010. Well, also for solving the radiative transfer equation was utilized the discrete ordinates method, and this method is intrinsically conservative because it does the balance of the heat flux and the heat source. So, the numerical method, the Chem1D software that has the transport equations. Also, it was based on the flamelet formulation proposed by Degas and with assumptions of laminar flame and low Mach number. Since it's 1D analysis, there was introduced a stretch rate K that accounts for the effects of multidimensionality. And here is the conservation equation, where the term for the strain rate can be observed. And this term of the strain rate that was varied along this research for multiple cases. So it was done a mesh conversions to analyze its independence. It was used 4 meshes, and it can be seen that from the 400 elements to the 800, there isn't too much of a change. So it was opted to use the 400 mesh for reduce computational costs. Here we can see the benchmark results for different strain rates. So with 5 different strain rates of 5, 10, 20, 50, and 100, it was simulated the case with the line-by-line integration method. So what is interesting to see is that the formation of carbon dioxide is more affected by the change in the velocity gradient than the formation of the H2O of the water vapor. So there was a decrease of 17% in the peak value of CO2 between the most extreme case, while for water vapor was only 3.4. and the temperature reached a peak at the 20 of a strain rate. So it was very interesting to see these results because changing the quantity of water vapor and carbon dioxide directly affects the radiative heat flux and heat source, as can be seen next. Here are the results for the radiative heat flux for these different strain rates, as well for the radiative heat source. Interesting enough, it can be seen that there isn't so much a change in the maximum value in absolute terms for the heat source, much like in the temperature, that doesn't change that much the peak. But however, for the heat flux, there is a great difference in the profile. So now we are comparing the different propositions of the WSGG with the benchmark result. In this work was applied 5 different propositions of the WSGG, which can be seen in these graphs. Interesting enough, it can be seen that principally in the radiative heat source, that two terms have a closer result to the benchmark. That is the Smith proposition and the Yin proposition. They are closely resembling the profile by the LBL. It is quite interesting, especially because these two methods did not benchmark the results with the LBL, while, for example, Dorigon's case was benchmarked with LBL. Here we can see the results in a table where you can see the maximum and the average normalized errors. So we have results of up to 20% for the Krishna-Murphy coefficients, while for Dorigon, the maximum result of the heat source was 17, which is quite interesting because the work proposed by him had previously achieved a relative error of at maximum 5%, but however, these were in decoupled solutions. And so, since we are dealing in coupled solutions of an iterative process, decrease in the formation of the species and of the temperature leads to a change in the radiative losses also. Also, another important factor was that all these 5 models, they were designed for a molar ratio specific of 2 to 1. And as we can see in this graph, the molar ratio is constantly changing. It goes from 3 in the fuel side and abruptly changes to 2 to 1 in the oxidant side. And interesting enough, the relative error has its highest peak right at the transition, which is also the flame front. So here, since the previous comparison was for one specific strain rate of 10, now we are analyzing all the 5 different strain rates that were analyzed in this case. So it can be seen, interesting enough, that although the models by Smith and Nin that have the closer result to the benchmark, neither of these models perfectly accompanies the behavior of the curve for the radiative heat source in the benchmark result. That is the one on the left. They have different peaks for the maximum value. Also, any other of the models also don't perfectly accompany the behavior. However, for the radiative heat flux, it can be seen that any of the 5 models can have a good evaluation of the profile for the heat flux. So, in conclusion, this paper presents an analysis of the accuracy for these different formulations. The results of local error of the model can be as high as 20%, and most models can adequately capture the behavior of the radiative quantities as the strain rate changes. So I would like to thank you for your attention, and if you have any more questions, please feel free to ask. Goodbye.